So now we're going to talk about the problem of how to solve a recurrence relation of this form. And by solve the recurrence relation, I mean find the formula for the nth term. The form we're interested in, just to begin with here, is where you tell me the first two terms of the sequence, a0 and a1. And then you tell me the recurrence relation for n greater than or equal to 2, how we express a sub n. In this case, we're going to talk about a linear combination, some constant times a sub n minus 1, the previous term, plus some other constant possibly, times the term before that. So if we have a recurrence relation of this form, is there a way to just get a formula for the nth term? And here's what I was just talking about. We notice that it looks like there's kind of geometric growth in these sequences. And that leads to the question, if it were exactly geometric growth, we would have this sequence r sub n. And when I write the sequence r sub n, I mean 1, that's r to the 0th, r squared, r cubed, r to the 4th, etc. Is there a sequence that really is a geometric sequence which satisfies our recurrence relation? We know from looking at those examples that they're not just geometric sequences by themselves, so they're not exactly of this form. But are there solutions to that recurrence, to this particular recurrence relation, ignoring the fact that the first couple terms might not be what we want? Are there solutions to this recurrence relation that are geometric sequences? Well, it's easy to check. We just plug in. If this sequence where the nth term is r sub n satisfies this recurrence relation, then a sub n, which is r to the nth power, must be c1 times an minus 1, which is c1 times r to the n minus first power, plus c sub 2 times r to the n minus second power. If we just divide out by r to the n minus 2, we get r squared equals c1r plus c2. This is a quadratic equation. And we know if we have a number which is a solution to this equation, then this sequence will in fact satisfy our recurrence relation by the work we just did here. So how many solutions are there to this quadratic equation? Well, in general, there'll be two solutions, but not always. Sometimes a quadratic equation has just one solution, and sometimes a quadratic equation has no solutions. What we're going to do today is talk about what happens when we have two distinct solutions to this particular quadratic equation. And let me give you some terminology. This particular quadratic equation will be called the characteristic equation for the particular recurrence relation that we're interested in. We'll learn later in the week what to do if there's only one solution to this characteristic equation. And I want you guys to think about it, and we can talk about later what happens if there are no solutions, what things look like. So what I said before was we're going to assume that this characteristic equation has two solutions. Let's call them alpha and beta, and here alpha will not be the same as beta. We're talking about two distinct solutions. Then we know that this sequence, alpha to the n, is a sequence which satisfies the recurrence relation. I'll rewrite the recurrence relation for n greater than or equal to 2. We want r sub n to be c1 r sub n minus 1 plus, I'm sorry, not with r's, let me erase that. We want, for n greater than or equal to 2, we want a sub n, the nth term of our sequence, to be c1 an minus 1 plus c2 a at n minus 2. There's our recurrence relation, and that will hold for this sequence, for terms of this sequence, and for terms of this sequence, beta to the n. So we'll have at least these two different sequences that satisfy the recurrence relation. Are there more? Well, my claim is yes. Any linear combination of these two sequences, if I let a sub n be some constant times alpha to the n plus some other constant we'll call capital B times beta to the n, I claim that sequence will still satisfy the recurrence relation. This is a very important theme in linear algebra, that you recognize linearity when it just kind of shows up. And is it obvious that this linearity shows up, that we have any linear combination of the two sequences will still solve the recurrence relation? Well, let's think about that. What if I, instead of writing this, I just look at a alpha to the n? We know that alpha to the n satisfies this recurrence relation. In other words, that means that alpha to the n will be equal to c1 alpha to the n minus 1 plus c2 beta, no, not beta, we're still looking at alpha here to the n minus 2. This is what it means for the sequence alpha to the n to satisfy the recurrence relation that we have above here. Well, if I multiply each term by a, the nth term of this new sequence isn't alpha to the n, it's a alpha to the n. Will that be equal to c1 times a alpha to the n minus 1 plus c2 times, and let me fix this up a bit. Now I'll want here a times alpha to the n minus 2. The answer is yes. You could just factor out the a, and the original equation holds, which we know is true. So this also works. When I say works, I mean satisfies the recurrence relation. And by a similar argument, of course, b times beta to the n also works. Now, let's say I have two different sequences, each of which satisfies the recurrence relation. So we know a alpha to the n is c1 times a alpha to the n minus 1 plus c2 a alpha to the n minus 2. We also know that for this second sequence, b beta to the n is c1 times b beta to the n minus 1 plus c2 times b beta to the n minus 2. What happens if I just add the left and right sides? I get a alpha to the n plus b beta to the n is c1 times a alpha to the n minus 1 plus b beta to the n minus 1 plus c2 times a alpha to the n minus 2 plus b beta to the n minus 2. Sorry, that's getting messy at the end of the board there. But the point is, if I know it's true for each of these sequences that they satisfy the recurrence relation, then I know it's true for a sequence whose terms are the sums of these, just by adding left and right sides of these previous two equations. So now I've got this whole infinite collection of sequences that satisfy my recurrence relation. And we ask the question, is the sequence I'm interested in the one that satisfies the recurrence relation and starts out correctly? Starts out with a0 and a1 at the beginning. Is that one of this form? And when I ask that question, let me write down the question here, is my original sequence, which starts a0, a1, and then continues, of this form. Where a sub n is a times alpha to the n plus b times beta to the n. Well, if it is of that form, when I just plug in n equals 0, I would get a0 is a plus b, and when I plug in 1, I'd get a sub 1 is alpha a plus beta times b. I would need both of these to be true at the same time. But this is just a system of two linear equations. In two unknowns. Here, think of the capital A and the capital B are our unknowns. A0, A1, and alpha and beta, those are all given, and we just have to find the capital A and capital B. Or here's a question for you. Have you learned when we can solve two linear equations in two unknowns? Is there even always a solution? Well, I'm sure you learned in Math 206 that in fact there always is a solution if the coefficient matrix, here's the coefficient matrix, 1, 1, alpha, beta, as long as this coefficient matrix is non-singular, then there has to be a unique solution. And then you might ask, is this coefficient matrix actually non-singular? Well, remember what we wrote down last time. We're assuming here that alpha and beta are different. We have two distinct solutions to our original characteristic equation. And when alpha and beta are different, you can easily see that the determinant is just beta minus alpha, which is not zero, which tells you immediately that this coefficient matrix is non-singular, and there will thus be a unique solution to this system of equations. And what does that mean? That means there will be a unique sequence of this form, where a sub n is a times alpha to the n plus b times beta to the n, which gets the 0 and the 1 term, the first two terms of the sequence, correct if you specified what those have to be. Does that mean that every other term will match your original sequence? If you give me a sequence, you tell me what the a0 and a1 are, you tell me the recurrence relation, I go through this procedure, find the unique a and b that work. Does that tell me I have the formula for exactly that sequence? Well, the answer is yes, if the first two terms are correct, and if your sequence with those two terms satisfies the recurrence relation, and my sequence with those two terms satisfies the recurrence relation, then every other term, one by one, will have to match between our sequences, and we'll determine, one can prove this just using induction, this is exactly what induction is about, that every term, every following term will be the correct term. And just as a quick aside, this is very similar to what you do in differential equations. Some of you, I hope, have taken Math 242, which is our differential equations class, and you'll learn that to solve, this is a linear second order differential equation with constant coefficients. If you have a linear second order equation with constant coefficients and you specify initial values, which are just a value of your function y at some particular point, it doesn't have to be 0, but I'll say it's 0. If you specify y of 0 is y0 and y prime of 0 is y1, then you ask, what can we find the solution to this differential equation that satisfies our initial condition? Well, in a manner that's very much analogous to what we just did, you can guess solutions to this differential equation. Ignore the initial values for right now. The solutions you might guess would be e to the rx, y equals e to the rx. And you would ask the question, for which r does this work? And if you just compute very quickly that the second derivative of y with respect to x, if y is of this form, is just r squared e to the rx, the first derivative is r e to the rx, you would immediately get, in order for r to work, or let me say it this way, r works, we can actually say if and only if r squared e to the rx equals c1 r e to the rx plus c2 e to the rx. We cancel the e to the rx's, which are never 0, and we get the equation r squared equals c1 r plus c2, and this is the characteristic equation for this second order linear differential equation with constant coefficients. It's actually homogeneous if you put everything onto one side. It's a second order linear homogeneous differential equation with constant coefficients. This characteristic equation is just like we had in our recurrence relation. And we can talk about what the you've probably learned, or if you haven't learned this yet, you will when you take Math 242, what you can say about the solutions when there are two distinct solutions to this characteristic equation, as we've assumed above for our recurrence relation, or if there's only one unique solution to this characteristic equation, which is a quadratic equation, or if there are no solutions. And in the case where you have two distinct solutions, then again, you'll have this linearity condition that if you have, say the solutions are alpha and beta, and you write the general solution as, I won't write this down here, but if you write the general solution as y equals a constant times e to the alpha x plus a constant times e to the beta x, you can solve for those constants using your initial values in exactly an analogous way to what we did above, solving for the correct coefficients. And all the same things will be true. It's not a coincidence that solving a differential equation of this form is very similar to solving a recurrence relation of this form. The recurrence relation, in some very important sense, is a discretized version of this differential equation. So the similarities are far from coincidental.